Are you getting what you're supposed to? The right-hand board has got the unit conversion part set up. What you calculate out there is going to be your energy. You'll use that value of energy to solve for frequency. And you'll use that frequency to solve for what? Now that wavelength is going to automatically come out in meter units. Automatically, because that's what you've got on the speed of light. It's going to fall out in meter units. The question does not specifically say it needs to be nanometers, micrometers, or whatnot, so leaving it as meters is perfectly fine. But it does have to have a unit, and that unit's going to be meters. Question? Question about any of this discussion with light? Concept or math?
Could you go over, could you write down the last one?
Sure. And this is what I'm getting in meter units.
In the exam, is it okay if we're off by a decimal machine?
Like what?
Just like you did.
One significant figure? It would be a small amount, like half a point or something. But now, the way you judge your significant figures is by your data. And this is the only data point you've got in the whole problem. H and C are constants, and constants don't limit you. That 1,000 with the decimal on it, that's 4 significant figures, and that's how you need to keep for your answer. Question? Yes?
Okay, on the sheet it says nanometers, not says meters. Does it matter which one?
Well, no. I mean, it just says what is the wavelength. It doesn't say what is the wavelength in nanometers. So if you wanted to leave it in meters, that's perfectly fine. What I did was converted it to nanometers, more out of habit than anything, but the conversion would look like this if you did it. Where nano is 10 to the minus 9. And that would shift out of meters and into nanometers. But that's not a necessary thing unless it says, you know, put your answer into nanometers. Other question? Any question about light? Concept or math? So ends the material for exam 2. I'll check. There should be one. There should be one under every category already.
Okay. There wasn't.
There wasn't.
I
All
did the
right.
same thing.
It's supposed to be there. I'll get that up there today.
Okay. Thank you.
Because it should have been there already. I'm sorry about that.
After this, I have a question about this topic. So, like, for example, on this page, this one asks us about the different types. So, like, when you're trying to do math, it's just going to be external questions.
Yeah. Explain why. Explain how covalent bonding works.
Okay.
Or something like that.
Okay. Thanks. I got mine.
Okay.
Yeah, I actually have them too. Yeah, we've already gone through that. That's part of the game too. And then put it off the thing here, they can do.
When we first defined moles, we had these two relationships. By name, Avogadro's number. Molar mass, where Avogadro's number was a constant and was the same for everybody, and molar mass was not. Molar mass depended on who you were talking about, and those were numbers we got off the periodic table. A mole of carbon would be 12.011 grams. A mole of magnesium, 24.305 grams. Those are molar masses. And we did molar mass, as I just stated, for individual elements. What we're changing in going into exam 3 is not so much changing, but I guess expanding. We're looking at molar mass of compounds now, as opposed to just single elements. So we're looking at what would be the molar mass of water, or what would be the molar mass of iron 3 chloride. This is made of 2 hydrogens and 1 oxygen, correct? And so the molar mass of the compound would just be the combined weight of 2 hydrogens and 1 oxygen. Molar mass of the compound is simply you add up the mass of everybody in that compound. And that tells you how much a mole of that material weighs. Terminology changes a little bit because when we were talking about elements, then we talked about atoms as being the smallest particle, a certain number of atoms of carbon. But when we're talking about compounds, the smallest particle of a compound is the molecule. Molecule implies bonding. Atom doesn't. And so we'll be talking about how many molecules of such and so rather than how many atoms. But that's a terminology difference based on the substance. It doesn't change a thing about the math. But there's no such thing as an atom of water, because water is a compound, not an element. There's 2 hydrogen atoms and 1 oxygen atom making up a water molecule. And the molar mass for that would just be the sum of those numbers. Now we have this thing called percent composition. Which is looking at a compound and divvying out that mass in terms of how much of it is due to each element. So just for a second, I'm going to abbreviate this a little bit much just for illustration's sake. But these hydrogens weigh essentially 1 each, correct? The oxygen weighs 16. So if we did treat that as whole numbers, which we shouldn't, but if we did, then that's a total molar mass of 18. Water has a molar mass of 18, and 16 of that 18 comes from the oxygen. And so if you were wanting the percent oxygen in water, it would be calculated as the mass of oxygen over the total mass of the compound times 100 to make it a percentage. Which, dealing with whole numbers, 16 of your 18 being oxygen. I'm getting 89%. Eighty-nine percent of water's weight is oxygen weight. Now for comparison, if we go back to that formula H2O, you've got twice as many hydrogen atoms as you do oxygens, correct? There's 3 atoms in that molecule, and 2 of the 3 atoms are hydrogen. You've got a lot more hydrogen atoms than you do oxygen atoms. But that's not the way percent works. In chemistry, percent is always based on mass, not the atom count. Because you can't go in the lab and count atoms. You can go in the lab and weigh things. And so it's always determined based on weight. And I guess if we wanted to calculate percent hydrogen in water, I guess mathematically it would be the other 11%, correct? Because percents add up to 100. But formally it would look like this. It would be the mass of hydrogen over the total mass of the water times 100. 2 over 18 is hydrogen. and that will solve out to be 11%. And that's kind of useful because that's telling you the breakdown of the water based on mass, and you can use that for any kind of mass. So for example, if we had 5,000 grams of water, then 89% of that 5,000 grams is oxygen weight, correct? You just take 89% of that 5,000 and you know how many grams of oxygen you have. Or 11% of that 5,000 grams is hydrogen. It's a good way to divvy out the mass in terms of how much is due to each element. Problem number 2. We've got 100 milliliters of water. We want to know how many atoms of oxygen are present in that 100 milliliters of water. You're given the density as being 1 gram per milliliter. This is your density relationship. Density relates mass to volume. We can figure out the molar mass for water. Now, a minute ago I used 18. If you keep the decimals, it turns out to be like 18.02. So I'm being a little bit more specific than I was in that first example. 18.02 grams of water being a mole. One mole of water being 6.022 times 10 to the 23rd molecules. This is Avogadro's number. And then each molecule of water has 1 atom of oxygen in it. This is really just your chemical formula. H2O has a single oxygen. So each molecule of water has 1 atom of oxygen present. So here's the mole relationships we used before. Molar mass relates grams to moles, but we weren't starting with grams, we were starting with milliliters, and that's what we needed the density for. And that last step is new, because that's where we're going from the total compound down to the individual atoms of that compound. Each of these formulas, well, each of these first 3 conversions we've used before. Not quite all piled up together, but we have used them before. So the focus here is that last parenthesis. because that's where we go internal on the water. One molecule of water containing one atom of oxygen. That's where we focus in on the oxygen part of the water. What if, just for pretend, what if you were asked 100 milliliters of water contains how many atoms of hydrogen? What would this change?
We change one atom to 2 atoms of
Good,
hydrogen.
very good. It wouldn't change anything until here. And at that point, we'd be saying each molecule of water has 2 atoms of hydrogen. But all of this previous stuff would be the same regardless. Because all of this stuff is dealing with water, milliliters of water to grams of water to moles of water to molecules of water. There's nothing in these first 3 steps that goes internal from molecules to atoms, right? And so if you're going from water to oxygen or water to hydrogen, that internal part is just in this one conversion factor. The rest of the problem is unchanged. Now I'm going to work this again in a different form. And this time really using essentially percent composition. If we have 100 milliliters of the water, each milliliter of water weighs 1 gram. This is still density. Now the molar mass of water, that 18.02 that I was listing over there, that's calculated like this. 2 hydrogens, 1 oxygen, adding all that up was the 18.02. And 15.9994 of that 18.02 was oxygen, correct? So 100 milliliters of water, each milliliter weighing 1 gram, and 18.02 grams of water would contain 15.9994 grams oxygen. 15.9994 of that 18 is oxygen mass, correct? This is your percent composition. And there we're going from the water to the oxygen part of the water. Question about that? That gets us to grams of oxygen. We want to get to atoms. The molar mass of oxygen. 15.9994 grams is 1 mole. And then Avogadro's number to go from moles of oxygen to individual atoms. Question. That's 2 different methods of doing the same calculation. It don't matter to me how you work as long as you show your work. Some people are going to be more comfortable with the top one, some people will be more comfortable with the lower one. You need to be able to do this kind of calculation, so practice both until you know you're comfortable with one or the other. They will both always work. So there's not a form that's better. It's just whatever form you are more comfortable with and therefore will remember better. Yeah, question? No, no question. All right. Any question? All right. The second page about empirical formula. As examples here, you're given a list of formulas. These are all carbon-hydrogen compounds. All 6 of these really exist. This is their actual molecular formulas. And the first thing we're going to do is convert that into what's called an empirical formula. And the different thing, I guess by definition, an empirical formula is a reduced ratio. You take what you've got in the molecular formula, you reduce it down to the smallest whole number ratio you can. So it's emphasizing the ratio of the atoms, not the actual number present. So let's reduce these. C6H6 would reduce to 1. A 1-to-1 ratio. So just CH, 1 carbon to 1 hydrogen, right? That's your smallest whole number ratio of the atoms. What about C2H4?
H2.
CH2. C6H12. CH2. C4H10. C2H5. And C4H8. CH2. All right. That's converting molecular formula to empirical formula. That is pretty much worthless. There's no chance that you would really want to do that. I mean, ultimately, you'd like to know the molecular formula. If you've got the molecular formula, why reduce it down to something ambiguous? Because notice, 3 of these compounds, they're very different substances and have very different properties, but they happen to have the same ratio, correct? So whereas giving the actual chemical formula is very specific, giving the empirical formula for that is a little bit vague. You're never going to be taking a molecular formula and taking it to an empirical. But very often what you will do is you do some experimental work to come up with the empirical formula, hoping that you can expand that out into the molecular formula. Because really, that empirical formula, if you look at CH2 as an empirical formula, then that's really giving you a list of possibilities of what the molecular formula could be. It could really be CH2, I guess. But it could also be this. It could also be this. It could also be this, etc., 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 correct? There's several compounds that have that ratio. So what we're going to be doing is taking experimental data like you would gather in the lab, turn that into an empirical formula, and then with a little bit of more information, make the leap from empirical formula to molecular formula. What we just did was a matter of definition. Experimentally, that's not worth much. But you will go the other way quite often. Question number 9. You've got a sample of a hydrocarbon. Now, hydrocarbon is hydrogen and carbon put together. That means carbon and hydrogen are all you've got. There's no other elements there. And in particular, in this sample, there's 1.154 grams of carbon, 0.290 grams of hydrogen. And we want to turn that into an empirical formula. Now, if carbon and hydrogen is all we've got, then I'm going to go ahead and write up here generically. This is our formula. Where X and Y are just generic subscripts for now. We don't know the numbers that go in there yet, but what we do know about the subscripts in the formula is they have to be whole numbers. And even though you'll never see units written on those, they have units of moles. So look at the numbers you're given and look at the two things about those subscripts that we're headed toward. We got to have mole units, but we're given grams. How do you get from grams to moles? Not Avogadro's number. The other one. Molar mass. Grams is a mass unit, right? Avogadro's number has nothing to do with mass. Molar mass from the periodic table does. So we got to get from grams to moles. I mean, we have a molar mass conversion to do, and also all those masses are decimals, and we got to shift things into whole number form. So there's two things to do: convert from grams to moles and make whole numbers out of it. To convert from grams to moles, we go to the periodic table. One mole of carbon would be 12.011 grams. 1 mole of hydrogen is 1.00794 grams. We convert each one by its own molar mass. That's molar mass conversion, nothing more. Now, obviously, that's not whole numbers, but we can make that into whole numbers. Comparing these two numbers, which do we have less of? Carbon. So if we take both of these and divide them by whichever one is the lesser quantity, the carbon moles divided by itself has to